Hello, class. We have seen that an electric charge exerts the force of attraction or repulsion on other electric charges. What factors affects the magnitude of this force? To find an answer, the French physicist Charles Coulomb investigated electric forces in the 1780s using a torsion balance, much like used by the Cavendish for his studies of gravitational force. That's similar to our experiment or demonstration we did in class. Precise measurements of electric charges were not available in Coulomb's time. Nevertheless, Coulomb was able to prepare small spheres with different magnitudes of charge in which the ratio of the charges was known. Although he had some difficulty with induced charges, Coulomb was able to argue that the electric force one tiny charge object exert on a second tiny charge object is directly proportional to the charges on them. That is, if the charge on either one of the objects is doubled, the force is doubled. And if the charge on both objects is doubled, the force increased to 4 times the original value. That was the case when the distance between the two charges remained the same. If the distance between them was allowed to increase, he found that the force decreased with the square of the distance between them. That is, if the distance was doubled, the force fell to 1/4 of its original value. Thus, Coulomb concluded the magnitude of the force F that one small charge exerts on a second one is proportional to the product of the magnitude of the charge on one Q, meaning charge, times the magnitude of the charge of the other, which we'll call that Q2, and inversely proportional to the square of the distance r between them. As an equation, we can write Coulomb's law as F equals K times Q1 times Q2 over r squared, where K is the proportionality constant. Q1 and Q2 represents the charges and r represents the distance. As we saw from Coulomb's law, this gives us the magnitude of the electric force that either charge exerts on one another. The direction of the electric force is always along the line joining the two charges. If the two charges have the same sign, the force on either charge is directed away from the other. They repel each other. If the two charges have opposite signs, the force on one is directed towards the other because they attract. Notice that the force one charge exerts on the second is equal but opposite to that exerted by the second on the first, in accord with Newton's third law. The SI unit of charge is the Coulomb, which we'll use the letter C for the unit. The precise definition of a Coulomb today is in terms of electric current and magnetic fields, and we'll discuss that later in Chapter 20. In SI units, the constant K is in Coulomb's law has a value of 8.988 times 10 to the 9th Newton meter square per Coulomb squared. Or you can just write it as 9 times 10 to the 9th Newton meter square per Coulomb squared, if you only need two significant figures. Thus, 1 Coulomb is that amount of charge which, if placed each on 2 point objects that are 1 meter apart, will result in each object to exert a force of 9 times 10 to the 9th Newton on the other. That's a large force. 9 times 10 to the 9th Newton is a very, very large force. So that weight would equal almost like 1,000,000 tons. We rarely encounter charges as large as 1 Coulomb. So it's very rare to see a charge that's 1 Coulomb. It's a lot of force. Charges produced by rubbing ordinary objects, such as like a comb or like a plastic ruler, those amount of charges are typically around a microcoulomb. Right? That's like times 10 to the -6 coulombs or less. Objects that carry a positive charge have a deficient of electrons, right? Whereas negatively charged objects have excess electrons. The charge on one individual electron has been determined to have the magnitude of about 1.6022 times 10 to the negative 19 Coulomb. And that's negative, so that's for one electron. That's the charge, times 10 to the negative 19. That is the smallest charge observed in nature, the smallest, and because it's a fundamental particle. It is given the symbol E, little e, and is often referred to as the elementary charge. Now note that this little e is defined as a positive number, so the charge on an electron would be negative E, and then the charge on a proton would be positive E. Since an object cannot gain or lose a fraction of an electron, right, the net charge on any object must be an integral multiple of this charge, right? So therefore, electric charges is thus said to be quantized, existing only in discrete amounts, right? Like 1 times E, 2 times E, 3 times C, and then keep going. Now, because E is so small, we normally don't notice this discreteness and microscopic charges. Like 1 microcoulomb requires about 10 times 10 to the 13 electrons. 10 to the 13 electron just for 1 microcoulomb. So we can see some continuous there. It's hard to see the discreteness. Now Coulomb law looks a little bit like the law of universal gravitation. If you remember that equation, that's F equals G, right, gravitational constant, times m1 times n2 divided by r squared. It looks very similar, you know, and that expressed the gravitational force on m1 and gravitational force of mass m1 exerted on mass m2. Both of these equations are the inverse square law, meaning that F is proportional to 1 over r squared. So both have the proportionality to a property of each object, mass for gravity and an electric charge for electricity. And they both act over distance. That is, there is no need for contact. A major difference between these two laws is that gravity is always an attractive force, whereas electric force can either be attractive or repulsive. Electric charge comes in 2 types, right? Positive and negative. Gravitational mass is only 1, which is positive. The constant K in the equation is often written in another term, another constant. It's called epsilon naught. That's a Greek letter, little e, or little capital E. It's an epsilon naught. And we call that the permittivity of free space. Again, it's permittivity of free space. That's what that epsilon naught's called. It's related to K, right, by K equals 1/4 pi epsilon naught. And so Coulomb's law can be rewritten as this, that you see over there. Now this equation looks a little bit more complicated, doesn't it? But other fundamental equations that we haven't seen yet are similar in terms of epsilon naught rather than K. Now it doesn't matter which equation you use, this one or the previous one. They're both equivalent. Now both of these equations apply to objects whose sizes, right, are much smaller than the distance between them. So ideally, it is precise for point charges. For finite size objects, it's not always clear what the value of r would be, particularly since charges may not be distributed uniformly around the object. If the 2 objects, let's say, are spheres, the charge is known to be distributed uniformly on each of those spheres. So therefore the r would just be right in the center of those 2 spheres. Now Coulomb's law describes the force between 2 charges when they're at rest. Okay, at rest. Additional forces come into play when the charges are in motion, and we'll discuss those in later chapters. But in this chapter, we're going to discuss charges at rest, the study with which we call electrostatic. Right? Static means still. Coulomb's law gives us the electrostatic force. When calculating with Coulomb's law, we usually use magnitudes, ignoring the signs of the charges, and then determine the directions of force separately based on whether the force is attractive or repulsive. Here's an example. Electric force on electron by proton. Determine the magnitude and direction of the electric force on the electron of a hydrogen atom exerted by a single proton. We'll call Q2, which is a positive E, that is the atom's nucleus. Assume the average distance between the revolving electron and the proton is r, 0.53 times 10 to the negative 10 meters. That's a pretty small distance. Now press pause and figure out how would you figure out what the magnitude of the electric force would be. To find the force magnitude, we use Coulomb's law. The electron and proton have the same magnitude charge E, so therefore Q1 and Q2 equal each other. The direction of the force on the electron is towards the proton because the charges have opposite signs, so therefore it's an attractive force. To check for the answer, go to page 446. Second example. Which charges exert the greater force? Let's say we have two positive point charges. Q1 is 50 microcoulombs and Q2 is 1 microcoulombs. They're separated by distance L. Which is larger in magnitude? The force that Q1 exerts on Q2 or the force that Q2 exerts on Q1? Press pause and think about this. From Coulomb's law, the force on Q1 and Q2 is represented by the equation below. And then the force of Q1 exerted on Q1 is represented by the equation below. Look at that. They have the same magnitude. The equation is symmetric with each other with respect to the 2 point charges.